So, I'm going to start this talk with a little confession. I'm a very new member of this group. I signed up last night because the Meetup website would not tell me the location unless I became a member. Okay, but I'm not new to Austin. I joined the UT faculty in 1988. That was 2 years after South by started in Austin, so they are having the 30th anniversary here. And what I wanted to do, since this is my first time in this audience, tell you a little bit about this journey that I had, because it informs what is happening in big data analytics these days. So my background was in high performance computing. And just at the end of my PhD work, I attended the first IEEE Neural Network Conference in San Diego in 1987. And I got really interested by these models. And I thought, well, OK, with high performance computing, you can make these things run faster. But you don't get more understanding of what these models do, right? So I got much more interested in the modeling and the statistical power of these networks rather than on making them run fast. Okay. Now, of course, after 30 years, with big data and the reemergence of neural networks in form of deep learning, it has all come a full circle, and both those backgrounds are coming to use. So what I did was, I think second year into my position at UT, I did something really stupid. I switched my area specialization into data analytics. Okay, which is actually something you should never do before you have tenure. Okay, that's what you do after. That's when you really can goof off. Okay, but that's what I did. But I somehow survived. And what I've done, and in the process, what I realized is that there's actually many communities, and I see some of them represented here, who try to get insights from data. Right. So there, of course, at that time there were the pattern recognition folks. There's, of course, then I discovered this whole community of statisticians with their own jargon and models, and very smart people. And then over time, the computer science community on machine learning. In those days, actually, machine learning was pretty much rule induction, inductive logic programming. It looked very different from what it is now. But more and more, they started dealing with numeric data, with probabilities, noise, uncertainties. So they changed quite a bit. Okay, there's also, of course, the social scientists, the ecologists, and so on, right? And there are lots and lots of very good tools out there. And I think the real challenge is that you have a bag of tools, you have a bag of problems. You want to figure out for your problem what tool or combination of tool works the best. And if needed, you forge new tools. Okay. And at that time, actually, I felt that understanding the data, representing the data, exploring the data is really key. And I think that realization is now much more common. At that time, people just wanted to run their statistical model on the data, right? But now there are lots of good models, but just understanding the data is key. And that's why I named my lab as the data exploration analysis. So exploration came first, and then the analysis part came later. So what we basically do is try to have data-driven insights and discover knowledge from data. And as professors, our job is to write papers, right? But I think more interestingly, we've developed many algorithms over the years that have solved real industrial problems and have made it to have been deployed in industrial or government settings. Okay, and one of the things I realized working with so many different communities is that there's no one size fits all, right? And quite often, the best solutions you get by mixing and matching and bringing multiple tools together. So I saw in the Spotify talk, there was an example of an ensemble, right? So that'll be a very simple way of bringing multiple models together. There are many other ways. So that's one of the things I've really tried to specialize it in what's called multi-learner systems, and actually an example of that. So these are basically trying to use multiple sources of data, knowledge, multiple methods of analyzing them and bringing them together. So one of the things I did a long time back, since we're in Austin, I'll give the example. So LCRA actually has a bunch of rules that tells you how to govern all the dams that are on the Colorado River and so on, right? So they basically have a knowledge-based or rule-based system. There's also a lot of climate data, there's rainfall data, there's flooding data. So what we did is we took the rule-based system and initialized a neural network type architecture, and then used historic data as opposed to rules to train that network and refine, and then we went back and we were able to get refined rules. And some of the refinements are actually, when you have rules, normally continuous variables get bent, right? So you say, okay, if Lake Travis height is between 680 and 685, blah, 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 open 3 gates, okay? But maybe it should be 687 and not 685, right? So some guy thought and said, well, 685 looks like a nice round number, right? Well, 2 feet is actually a lot of water, right? Because it's 2 feet multiplied with the area of Lake Travis, which is quite a bit. Okay, so actually that was one of the best paper awards we got. So that was an example where we used a symbolic reasoning system with a connectionist or data-driven system to solve a problem. Okay. So what I wanted to do is give you. By the way, I'm in ECE department, but I've noticed 3 people from my McCombs class, right? Matt, 2, 3, right? Greg, yeah. So I've actually, a few years back, I helped the business school start this master's program in business analytics, and I teach a course fancifully called Advanced Predictive Modeling, right? Yeah. And it's been actually really fun, interacting with the business school students, because they always think about, what can I use this for, right? And how do I make money out of this? So, and they're also very interested in the technical aspects. So it's been actually a very, very nice experience. So, okay, so 3 people here. Okay, good. So what I wanted to do is to give you a flavor of the kind of work we are doing, giving examples from 3 very different areas. Okay, and that's one of the nice things we have. You have 12 PhD students, you can actually work in several areas and have more fun. Okay, and you'll see that the variety of techniques we use are actually quite diverse, and it's basically driven by the problem. Okay, we try to understand the data. What are the issues with how the data was gathered? What are the kind of insights we are trying to get, or what are the business problems we are trying to solve? And then we start thinking about how to build the right type of models. Okay, so the first application is from the healthcare industry. The second is from oil and gas, since we're in Texas, and the third one is ranking recommendation ratings, which I guess a lot of people that touch a lot of you, right? Okay, maybe I'll say a little bit about the limits of big data. Maybe I should not, because South by Southwest is all about hype also. So maybe I should not, we'll see. Actually, there's one of the companies I'm on the advisory board of, they're having a South by session, and I think the session is called, Will Austin's AI Rule the World? I said, okay, that's a very South by type. Okay, so I'm surprised they didn't say universe, but okay, just the world, right? Okay. All right, so the very first thing is about something called trying to get phenotypes from heterogeneous health records. Okay. So what are phenotypes? So phenotypes are basically manifested characteristics. So there could be characteristics of organisms, of disease, etc. Okay, they're not raw features, but they are at a level that a clinician understands them and can use them for their day-to-day activity. Okay, so if you give clinician a bunch of measurements, that may not be of interest, but you can say, okay, this guy has the phenotype for type 2 diabetes. The clinician knows how to interpret that and use it. So as we move very drastically into electronic health records, and the adoption in the country has gone from like 15% to over 90% in about 5 years, which is pretty amazing. There's been a lot of interest in trying to get phenotypes from electronic health records. Okay. So, so this is an example of diverse data types. So depending on what kind of data you're going to get different types of phenotypes. So here I'm looking at a phenotype for acute liver injury. So I might be just looking at diagnosis codes, or I might look at diagnosis plus procedures, or that plus lab, and so on. So depending on how many type of data sources I look at, I get richer and richer phenotypes. And the phenotypes are basically and kind of rules. If A and B and C or D, then this guy has acute liver injury, right? And typically then there's a whole list of exceptions. Okay, so this is one example. So occurrence of one diagnosis code, and there's a list of codes that will match. And this has done, so there's a timing aspect. This happened 30 days back. This happened 60 days later, and so on. Okay, so it's a fairly succinct and clinically meaningful information that a clinician understands and can work on. Okay, so how do they come up with these phenotypes? How much effort do you think is taken to get one of these? Okay, so there are actually many national level efforts. So these are big dollar efforts. They involve 10 institutions and 50 clinicians and so on. And you form a committee, and then you grill experts, blah blah. It takes typically over a year with many human experts involved to come to a phenotype. And then of course you go to another hospital, their coding system is a bit different and it does not apply. Okay, so it's a very useful thing, but it's a very, very labor intensive process. Okay, so we are saying, well, we have very little idea about healthcare, but can we try to think about this in machine learning terms? Okay, so how do we do it? So here's basically what we started doing. So this is an illustrative example. In fact, the first experiment we did was data from Geisinger, and that had a whole bunch of patients which are mostly on conjunctive heart failure type patients. And for each of those patients, we had their diagnosis and the various procedures done on them. Okay, so you can think of this data as a cube or a 3-mode tensor. Okay, so now what you're trying to do is, well, I have my data as a cube, and the reason you don't want to flatten it out, because then similar diagnosis, if you flatten out, might get straddled, right? Just like if you convert an image into a one-length vector, then consecutive columns will be actually quite spaced apart, right? So you lose a lot of this domain interaction. Okay. So now think of this as just an extension of doing PCA. So in PCA, what you do is you have your data. You can think of it as a matrix, and then you have the principal components ordered by the corresponding eigenvalues, right? So the lambdas would be the eigenvalues, and then so this is what's called the spectral decomposition of a matrix, and each little rank 1 matrix here for principal components would be the corresponding principal direction multiplied by the loadings, right? So there will be a principal direction of the loadings. That will give you the first one. So this is for the first principal component. This is the second one, third one, and so on. Okay. Here it's a tensor. So instead of having an outer product of 2 vectors, I have 3 vectors, right? But conceptually, it is very similar. Okay. Now, is anybody here work a lot with tensors? Okay, good. So you know that actually tensors, nothing is easy. So even SVD type properties don't work. So actually, as soon as you go from a matrix to a sense, all hell breaks loose. So it's not so easy. But in terms of conceptualizing what we are trying to do, we are trying to represent the entire patient population using a small number of factors. Okay. Now, there are some constraints because these numbers are all positive numbers. So we cannot do a regular PC kind of decomposition. We have to use a Poisson model. So all the numbers are non-negative. We want these factors to be sparse because we want very few things to be on, because then each component can be easily explained. Okay, so that's where all the domain constraints come in. So what this is really a sparse non-negative tensor factorization using a Poisson regression model. Okay, but it's kind of a generalization of PCA. Now, if you do that, then you can think of the entire patient population is kind of being explained by a few factors, and each of them is a potential phenotype. Okay, so here's an example. So this may be one of the factors. And these are the patients for which this factor is important. So in the PCA analogy, these are patients that are kind of aligned in that principal direction. And these are the non-negative terms. Now you can just read them out. And you say, OK, with this diagnosis, these are the procedures that go together. There's more detail here. It's just written in English. And this is a phenotype. Now remember, there's no human expertise culling this. So this will actually have to now go to a committee, and they will refine it and so on. So this is not a phenotype you can run with. But what we've done is, by a fairly mechanical way, we've generated a whole bunch of potential phenotypes that now experts can run with. And maybe what took more than a year person effort for one phenotype, now we've generated 50 phenotypes which somebody can examine in a short time and act on it. Okay. So actually, the first work we did with Geisinger, we actually had to run these by clinicians, because sometimes you just find something in the data, but it's actually not meaningful. And if doctors can't understand what you did, there's no way they're going to act on it. Okay. So 42 out of 50 were actually clinically meaningful, and some of them represented new knowledge. And that's pretty amazing, because this was pretty much knowledge free other than the mathematical constraints. So this is actually part of now a very big effort, where what we try to do is we generate phenotypes, and not only having just the data that I said, you also have clinical notes, you have labs. So there are a whole bunch of tensors and matrices connected, and you can collectively and jointly factorize all of them. Okay. Then you can have physicians look at them, refine them. You can refine them algorithmically too. For example, you can seed some of the phenotypes based on knowledge that you already know, right? You also want to see how they go across hospitals, and then you want to apply them for various types of predictive tasks. Okay, so this is my first example, and an example again we are using a whole bunch of methods. How to seed models, how to do factorization, which is a standard machine learning technique, but how to do domain adaptation, which is more of an AI type technique, and so on. Okay, so I am going to actually, my student who primarily worked on this she had a healthcare startup here, but she just joined the faculty at Emory, which is great because that's where CDC is. So that's like an ideal place for her. Okay. Okay, so this is my second example. So, well, one of the insights was, the oil industry is in big trouble, right? But even when they're in very big trouble, they actually have a lot of money, and even if they put a little bit of that to research, it can pay off very, very well for them, right? So now they're trying to recalibrate the industry for a $40 barrel oil as opposed to 110. Okay, so they are trying to re-examine all the data they have and see what value they can extract from this data. And they actually have a lot of data. This is just sensory data. They obviously do a lot of physical simulation, reservoirs and so on. So a few years back, 2 years back, I talked to the CTO of Schlumberger, and they had a facility with 50 petabytes of storage, petabytes. Okay, but most of that was simulation data. But what has really changed, I think, very recently, the last 3 years, is this distributed acoustic sensors. So these are fiber optic sensors that can go into the borehole. Okay, and every few meters there's an acoustic reading. So now you have a huge spatiotemporal reading across your oil field, because you have reading every so many meters down, and then you have across, and then over time. Right? And before this, this information would be sent by telemetry, which would be a few kilobytes a day. And now once the fiber optics has come in, now they're getting a few terabytes. It's about 8 to 9 terabytes a day from a reasonable sized field. So they've moved suddenly from a few kilobytes to terabytes, like they kind of jumped a few orders of magnitude there, right? So they're saying, well, what can we do with all this data? Okay. So here's an example of some of the sensory data. So here, this is depth, and this is time, and then several events are happening which is of interest to them. There are actually a lot of applications of this. And right now they basically have a display, and they have one guy who's very sleepy, and he's just keeping on looking at this display, because most of the time nothing interesting is happening, right? Okay. So we've been looking at this problem and tried to see where events of interest happen. And as you can see, it's just not modeling. There's a lot of data filtering going on. There's a lot of signal processing that's going on, and so on, right? You can't even afford to store this data for more than a few days, right? So it's very, very rich data. But from the machine learning viewpoint, what's I think most interesting about this is a very nice venue to explain or illustrate, multitask learning, knowledge transfer, ideas like this. Okay, so basically what's happening is they have lots of data, but they have very few operators, sleepy ones, and there's very little labeling of this data. Okay, so you spend some money, you've got some labels from one rig, but now you have to suddenly realize you need to build a model for another rig. Okay, so how can you leverage what you learned here to jumpstart the model for that, which is actually slightly different? No two rigs are exactly the same. Okay, and once you've done this for one particular what's called a play, how does that relate to new rigs you want to do for another play? Okay, so there are ideas of knowledge transfer from one set of models to jumpstart a second set of models. Okay, so I'm going to explain all these at a very high level. If you're interested in more details, I can throw a lot of math at you. So, okay, all right. So my final example I wanted to cover is this is actually a very broad. It's basically getting determining preference order among a bunch of objects. So I'm looking at the recommender system example because I presume all of you have seen this, right? So I have movie recommendation thanks to Netflix. Everybody knows about this problem. So do you think the Netflix competition was good for the industry, or this area, or bad? The $1 million prize. Any thought?
Put it on the map.
Sorry?
It certainly put it on the map.
It put the area on the map. It also put Netflix on the map. I think that was the best marketing dollars they ever spent. Okay, it got a lot of people interested, students in machine learning. So that was great. Unfortunately, the lessons learned from Netflix, people read too much into it because the design was very flawed. Okay, and many people have just the wrong idea of how to do recommendation correctly. Okay, and this is a long story. I don't want to delve into it. But basically, if you think about, for example, the criteria, okay, the idea was to minimize root mean square error. Okay, so firstly, square error the right cost, and secondly, it is computed over all ratings. Okay, but think of any recommender system. You actually don't care what I think about the zillions of movies that you offer, right? You actually care about maybe the 20 good movies this person would like to see, right? And you don't care about how accurate you are on the rest. Okay, I actually gave a talk at Amazon, and they certainly know something about recommendation. And they just said, tell me the precision at k results, right? They just want to say, okay, if you recommend 10 things, how good are those recommendations? Okay, so the cost matrix that they used is actually flawed, and hence any solution that does well. In fact, there are papers now written showing that you're actually going to do much worse on precision at top k, even though on mean square error you're doing better. Okay, but anyway, so I wanted to illustrate, and one of the approaches that got famous in the process was matrix factorization. So I'm going to represent this matrix of given ratings into a product of two long skinny matrices, right? And the entries of these matrices, that's what I basically learned. And then any entry here, the known entries I'll try to approximate using the matrix product. And then of course these matrices are full, so now I can get any of these empty boxes, and that's how I get all the scores, right? Actually, matrix factorization tries to minimize the sum square error, which, as I said, is not the right thing to do. Okay? But there are many other problems with this, and one of the problems is that is the gap between a 5 and a 4 the same as between a 3 and a 2? Not really, right? Because it just says 5 is higher than 4 and 3 is higher than 2. But in my mind, the gap between 3 and 2 may be very different from yours. My 5 may not be the same as your 5. Okay? So really, you should think of these as imposing an ordering. And you can only reason about ordering within the same person and not across persons in terms of the numeric score. Okay? So those are two of the issues with the Netflix type of idea, and hence with matrix. So as you know, the winners basically had a bunch of these matrix factorizers put into an ensemble with some other techniques as well. But that's the top two solutions both did the same, right? So that led to a lot of people running in that direction. Okay? All right. So we basically said, and this is actually one instance of an ordering problem, because for every user, I want to rank order all the movies and then look at a criteria that focuses on the top of the rank ordering. Okay? So how do we attack this? So actually, if you have okay, so I see Clint is also there. He worked for a while in my group looking at this, where you also want to make use of properties of the users and properties of movies, so the so-called side information, right? And in big data scenario, what's happening is, what's really growing is the variables associated with the rows and columns, right? This is actually the outcome matrix. Okay? So if you go to Google or Yahoo, they have thousands of features for every user, and of course they have lots of rich data about the products. Okay? So if I could think of these as scores and predict them using my various features, then it's a nice regression problem. Okay? And regression actually is fast. At least linear regression is quite fast. Okay? But you know, these scores, as I said, you should take them with a pinch of salt, right? So what we realized is the order, just the order matters. Then you can move the scores around so long as you don't mess with the order, and that might actually allow you a much better fit. Okay? So this led to an idea. These are actually all the examples I'm giving are current projects. An idea what I'll call monotonic retargeting. And it actually has lots of applications. We are looking at aggregated data, learning to rank, like ranking results of a search query, survival analysis, and so on. So there are actually many, many applications. And the simple idea is as follows. Suppose x is my independent variable, y is what I want to predict, and my data looks like this. Well, if my model is like a linear regression, that's tough to fit, right? But I can say, hey, I can futz around with y, so long as I don't flip the orders. So I can have new y's that look like this, right? So actually, this is going to sit on top, but it doesn't matter, just the order matters. I've maintained the order, but now I have a much simpler model that fits very well. Okay? So putting it in slightly more abstract terms, so normally one way of thinking about say a regression model is that I have a target score vector right there, right? Because all the data points I can think of all the y values and make a long vector. So that's my target score vector, and depending on what weights or betas I get, my coefficients, I can get any solution in this space. Okay, so typically what like least squares will do is to find the solution, and this is my solution space, which is closest to that guy. Okay. However, what we are saying is I can actually change that score vector so long as I don't change the ordering. Okay. So now I can say, well, my score vector could be anything in this space. And now I can iterate, updating not only my model parameters, my betas or my weights, but also the independent variable values, right, the y values, right? And this looks very daunting. Why? Because I actually have infinite possible scores that are equivalent in ordering to that score. Okay? But actually, it turns out this is a convex cone, and I'll skip the math, but basically it's very easy to characterize, it's very easy to solve. It can be solved for a very large class of loss functions called Bregman divergences. And that's important because people have shown that for a ranking criteria, that's the only class of loss functions that is statistically consistent with that ranking criteria. So there's some nice properties of this function. But basically, you update your model parameters using a GLM solver, and then you update the scores, right? Which is basically I am, for example, changing from these scores to these scores using something called a PAV algorithm, which is actually very fast. Okay, so there's all this math behind, but the outcome is an algorithm which is actually very simple and scales very well. Okay. I don't know if anybody, let's forget this. Okay, this basically says for, even if I don't know what this, the transfer function for a GLM is, I can tell you how fast it's going to converge, and there's going to be a log n penalty. Okay, and the exact convergence rate depends on how curvy that function is, but each case you can come up with some convergence rates, and they're all pretty fast. Okay. So that was my final example, and I hope these 3 examples give you some idea about how you deal with big data problems. These are all, the scalability is one aspect of all of these applications. And shall I say something about problems with big data? Actually, I want to mention something. So the Michigan Democratic race, Clinton was up by 20 percentage points, and she lost. And I see people saying, oh, they didn't use big data, so the sample sizes were too small. Okay, so do you think that was the problem? Yeah, so actually with samples, with more sample size, you can decrease the estimation error of your sampling, right? But you cannot change the bias of your sample. And among many other problems, their sampling was very biased, because they used phone calls on landlines, right? And okay, so now you know where I'm going with, right? Now think about Bernie supporters and how many of them have landlines are going to respond to you. Okay, they also did not sample the independent voters, right? So one has to realize just not, okay, if I have more data, I would have done it correctly, right? So this is actually a very nice article I saw in the Financial Times, which talks about many of these aspects. So big data is great, but you still need to watch out for, I think the most important thing is a lot of big data is not generated by controlled experimental design. A/B test, of course, is, but many of the others are not. And so you need to understand how the data was obtained, right? And that's why I go back to this idea about data exploration being very key. Yeah.
I mean, let's assume that they knew what they were doing, and maybe every once in a while, someone young would have picked up the phone from a landline.
Right.
They could have weighted those results.
Yeah. So you could have done important sampling, and then you want to figure out whether this person is young, and but you really need to know the proportion, because the question is, you don't have to be just human, but you actually have to be somebody who goes and votes, right? So knowing that proportion is not so easy. Yeah, but that would have been a good start, a good step. And this was a lesson in the 1936 election between Roosevelt, FDR, everybody knows, and Langdon, who nobody knows because he lost. Okay, and basically this company, some magazine, polled, and their data was 8 times the size of the Gallup poll. But the way they got the poll records were from people who owned automobiles and phones. And in 1936, that was primarily very rich people. And they were much more for the Langdon guy than for Roosevelt. Okay, so they had 8 times the amount of data, and they came up with the wrong result. Okay, but and that was in 36, but in 80 years, people haven't learned the lesson, right? So anyway, so I wanted to close with something. So former ECE students might be interested. So if I look at machine learning proceedings now, they remind me of proceedings in like signal processing conferences. Stochastic gradient descent, convergence rates, streaming data one at a time, optimization. These are very traditional EE type concepts that you see in like adaptive signal processing, adaptive control type classes, right? And we suddenly realized, well, I was in this area for a long time, but many of my colleagues are saying, oh, we were doing machine learning all along, but we just didn't know it. Okay. Well, tongue in cheek, actually, there are a bunch of I have many colleagues who have regular papers in ICML and so on. So we've started a data science in engineering initiative in our department, and we are about to launch an undergrad track in data science in an engineering context. Actually, I'm teaching an undergrad now, and so interestingly, so a multi-layered perceptron was not there in scikit-learn, because I guess those guys are too young to realize this was a very popular model once upon a time. So I made them install TensorFlow and have a deep network with only one hidden layer. It's not so deep, right? And hence simulate a multi-layered perceptron, right? So we are actually having students who are being trained in this way. There's a lot of interest from students. So this might, I think many of the entrepreneurs here might be thinking of this as a potential future resource. So with that, I think I shall shut up. Okay, thank you.